Excellent. Good afternoon, everyone. Thank you very much for joining this webinar, the final webinar of the project Advanced Planning of PV-Rich Distribution Networks. It's a pleasure to have you all. We have different stakeholders joining us today from DNSPs, from people from government, researchers, etc. We hope to really give you not just the gist of what we did in the project, but the most important thing, our planning recommendations here for perhaps having in the future really high penetrations of residential solar photovoltaics in Australia and international as well. We will have around 50-minute presentation, and we will have plenty of time for questions and answers. So please use the chat box to ask any questions. So don't wait until the last minute. Put your questions, fire your questions. We will be recording everything in the chat, and we will go through them. Also, if there's any technical issue, please just mention in the chat. We will keep an eye on that as well, so we can sort it out. You will be muted throughout the event, but of course, during the Q&A as well, you can talk if that's what you wish. And of course, we're recording this webinar, and more importantly, we will make it available as well later on for yourself and anyone else that might be interested. So let's continue. So this particular webinar is really the consolidation of findings of the project that started 2 years ago. It will be presented by myself, Nando Choa, professor at the University of Melbourne, and Dr. Will Nagmanson, a research fellow that also you can see there as one of the hosts in this webinar. All right. All our projects and publications are these links. I mean, we will provide the slides as well, so you don't need to remember them. Anyways, although Will and myself are the project team right now, we had other members as well that supported the project throughout as well. So we will thank them as well later at the end of the presentation. So what we're going to go through today. So first, I would like to present the context, not just general context that yes, we have potential impacts, from having lots of solar PV in our distribution networks, not just the basics, but discussing really from the perspective of increasing hosting capacity. And also to be sure that we are all in the same page, I will provide some definitions. Then we will move on to the project summary, really just the overview of what we did, but then going a little bit more in detail, presenting tasks 1, which was really the modeling that we did of the integrated high voltage, low voltage feeders that we selected with OSNet for this project, and tasks 3 and 4 that are really the traditional and non-traditional solutions, the impact analysis, 5, the cost comparison, and 6, that really consolidate the findings. And then eventually we present the planning recommendations that we will be discussing, and the recommendations as well for advanced calculations. Now, this is quite an interesting presentation to do, because we will try to give you the main points of what we have done in these 2 years. But before we start, of course, I need to acknowledge that this project received funding from the Australian Renewable Energy Agency, ARENA, under its Advancing Renewables program. And also, I need to mention that the views expressed herein are not necessarily the views of the Australian government, and the Australian government does not accept responsibility for any information or advice contained herein. It's just my responsibility and Will's responsibility. Excellent. So, what is the context that we are in right now? It is the connection of technologies, in this case, solar photovoltaics, to networks, the distribution networks that have not been designed to have those technologies in place. We designed distribution networks like the low voltage, those that connect our houses, the streets, and to cover, to really be able to deal with demand, with the peak demand. And that means that, during those peak demands, well, the assets are capable of handling the corresponding currents or power flows, and the corresponding voltages are all within the limits. However, when we have photovoltaics in a weekday, for instance, where no one is at home, we will have what it is called reverse power flows, because this is power now being injected to the grid. It is going the other way around, because now we are little generators. And because there's a coincidence, because the sun shines to everyone simultaneously, and no one is at home, so you will have a coincidence of reverse power flows that can, in the aggregate, result in reverse power flows that, in terms of magnitude, the current can be much larger than the assets that are there, the conductors, the transformers. And in terms of voltages, you will have an effect that is called voltage rise that can even go beyond the statutory limits. So when people are not home and photovoltaic generation happens, we might have problems, not all the time, of course. And this is not just in the low voltage networks, this is as well in our high voltage networks, 22 kV networks or 11 kV networks, 33 kV networks. Why? Because of course you have just the aggregate effect of these urban areas. Or well, neighborhoods, if you want. Of course, it's not as dramatic as it might look in this little illustration. In reality, we have commercial buildings, we have industrial buildings, they will absorb reverse power flows, but it's just to illustrate the fact that we would have this problem in direct. And actually, as a matter of fact, DNSPs across Australia are very aware of this, so much that at some point, some of our zone substations, internationally called primary substations, they are already seeing these reverse power flows. So we have these problems, we are very aware of them. But the question really, as much as there are some solutions here and there that are being utilized, is how can we actually increase the hosting capacity of our networks? How can we make sure that we can make the most of our assets, or with added assets, we can make the most of these networks so we can have really, really high penetration of photovoltaics? Now, before we start discussing all this, we need to have some definitions really in place. What is hosting capacity, particularly when we talk to about solar photovoltaics? So this is the maximum amount of solar photovoltaics that a given distribution network, or part of it can be just a street, can host without negatively affecting its normal operation at any point in time. What is normal operation? Some might wonder. Well, normal operation is when our voltages in the network are within the statutory limits, the utilization of our assets, our conductors, our transformers, they are not overloaded, they are not congested. And of course, there are many other things such as harmonics or protection. In this particular project, we focus on voltages and asset utilization only. Now, what is this amount of solar PV? There are different ways of quantifying this. In this particular project, we refer to the percentage of residential customers with photovoltaics. So if we're talking about 50% penetration, we're talking about that 50% of the houses in a given network have photovoltaics. But there are different ways of quantifying this. It can be the total installed capacity with respect to the capacity of the zone substation. There are different ways of quantifying this. And we will also use a term called solutions. And we are going to differentiate them into two mainly, the traditional and non-traditional. The traditional ones are implementable solutions, all right, conventional solutions that distribution companies, our distribution network service providers, DNSPs, such as AusNet, that is co-funding as well this project, use already or can use in the near future or almost immediately to increase hosting capacity without significant complexity. On the contrary, a non-traditional solution will be a solution that a company, distribution company, could use, in theory, to increase hosting capacity, albeit with some added complexity, right? I know that the definition can be a little bit vague depending on the technology we're talking about, but let's use this for now. So let's discuss this traditional and non-traditional. So traditional, just to be a little bit more tangible, if you want, is, for instance, augmentation. Or as in America is very well known, they use the term wires alternatives, which is essentially replacing conductors for larger conductors, so you can have more ampacity, more currents. The benefit of that as well is that with larger ampacity, you have lower impedances, and that can have some benefits with voltages as well. You have larger transformers. If you have many flows, larger transformers are needed. So that's augmentation. We can have better setting for our low voltage on-load changers. So our distribution transformers have off-load changers, not all of them, but those that have, we can have better settings. We can have better settings as well for our zone substations on-load changers. We could have different inverted settings based on standards to define exports or the volt-watt functions of volt-watt functions. So this is what we call traditional. What is non-traditional then? So for instance, actively controlling either with remote measurements of smart meters or just local measurements, but something different in our zone substations. So this is already something that some companies here in Australia and other parts of the world are already testing and making it part of their business as usual. We could use low voltage on-load changers. This is a technology that already exists for many years, but although it might be very effective, it still is perceived as expensive. And this is what we're going to discuss as well today. We can actively control PV inverters, sending signals. There are projects already in Australia doing this as well, but still there are many questions about the technical aspects and also the cost. How much does it cost to put all this together? And same thing with batteries. So in general, what we refer to as traditional are what distribution companies are already doing, right? And the non-traditional, well, distribution companies are exploring. So there might be trials, but still, we are still learning what are the total advantages of this. Now, the big question would be, which are the most cost-effective solutions? Well, the reality is that it is not that we can pick one or another. Why? Because a single solution will not necessarily cover all the corresponding technical challenges that we will face. So for instance, just increasing the wires, the conductors or transformers might solve, of course, the ampacity problems, meaning you can have larger currents, the reverse power flows, but not necessarily solves the voltage problems, depending on how the impedances are changing. Managing the off-load changers or the on-load changers definitely will help with voltages, but will not help with acid congestion issues. Same thing with the PV inverter settings. Our standards are really there, to help us managing voltages most of the time, but not necessarily the aggregated currents that we're going to see the moment that we have many neighborhoods exporting power. Same thing with the non-traditional. You will have some solutions that might help with voltages, but not necessarily with congestion, or some solutions might help with congestion, or depending on how the solution is implemented, might help with congestion and with voltages simultaneously. So it is not a single solution that we have to look at. So one solution does not always address all the issues. It depends on the problems, and also it depends on the networks. A rural network might benefit from certain solution much more than an urban network. And also it depends on the timeline of PV adoption. A solution might be great if you're looking at really, really high penetrations in the future, but if you're looking at a network that for whatever reason will not go beyond 30% of penetration, perhaps 30% of the houses with photovoltaics, then you might not need the super duper solution. You just need something simpler that will end up being more cost effective. So we need to capture all these aspects when really making these recommendations. And this is what we try to do in this particular project. And yes, bottom line, there's no silver bullet. I believe that the DNSPs know that very, very well already. So the right question would be, which is the most cost-effective mix of solutions for a given PV penetration, the desired PV penetration, either 100%, which is perhaps too futuristic, but whatever it is, the number, and a given type of network as well. What works for rural doesn't necessarily mean that will work for urban, and whatever is in the middle as well. All right, so for a solution to be successful, we need to manage many technical aspects, but at the very least, voltage and acid congestion. And something very important as well, we need to do this with minimum curtailment. So making the customer not be negatively impacted in their ability to generate power from the sun. So having all this is not that easy. So we need to carry out different assessments to really quantify this. And of course, any solution that will help us increase hosting capacity that ticks all those boxes also needs to offer good value for money, which makes things more challenging. So I'm not going to tell you what solutions that I'm going to present here to contrast these values of an urban feeder at 100% penetration, where you can see here the customer voltages are already beyond 1.1, and then the transformer utilization at the low voltage, the distribution transformers are already congested. The moment we put another solution, you have all these metrics, all this performance going in a much better way from a technical perspective. And from the perspective of the customer here, I don't know where you can see my mouse here where it says PV active power or the curtailment. What you see here is that the ineffective solution will make most photovoltaic systems curtail, all right? Because voltages are too high, and we are following, for instance, the PV inverter settings here in Victoria. But if we have an effective solution that is managing the voltages of the network in a much better way, then these photovoltaic systems will not curtail so much. And that's good, because it means that people will make the most of their photovoltaic systems. So that's what we want with an effective solution. That is not only looking at voltages, it's also looking at utilization of assets, and it's a combination of things eventually. Now, other considerations that I want to make clear here, because this project eventually compare not just the technicalities, but also the cost of the solutions, we need to have an understanding of both aspects of any solution that we consider, cost and technical. So despite the fact that there are many innovative solutions being tested around the world and within Australia for the sequestration of distributed resources and photovoltaic systems like dynamic settings, export limits, etc., those solutions have cost and technical aspects not yet very clear for comparison purposes. So that's why we didn't consider a very futuristic solutions in this particular project. Also, when we are analyzing all these solutions, we took the point of view of the DNSPs. So the idea here is to really focus on the necessary related investments for the DNSPs, and of course the effects on customers as well. As mentioned, curtailment was the main metric here. Of course, if voltages are all okay, it's okay for customers. But we're excluding potential externalities because we don't know what happens in a future where 50% of the houses have photovoltaics. Of course, we will have implications in the cost of electricity because of the wholesale market. Those are externalities that we're not considering here. We're just looking at the DNSPs and the poles and wires within their networks. Okay. Now, with that said, I already spent 15 minutes, but I hope that that was useful just for you to understand, what is the context of this project. We ran this project from February 2019 to this month, and we ran these 6 tasks, from the modeling of specific high voltage feeders to innovative analytical techniques, traditional solutions, non-traditional cost comparison, and the consolidation findings. So we completed this project, and now we're presenting, well, the main findings to you guys. Let's start first with task 1. I'm not going to present all the findings here, just to let you know what are the networks that we consider here. Of course, in the case of OSNet, they have hundreds of primary substations, and then therefore you multiply this by the number of feeders that you may have, then you end up with really hundreds of high voltage feeders. So we couldn't model everything. So what we decided is to model the most extreme cases. So rather than doing the typical cases, we went for the most significantly different characteristics, and we end up with 4 feeders. These feeders are what you can see here: the show rural, urban to urban, and then along rural as well. Now, this was done based on an analysis of all the feeders and different characteristics, and of course, as well, availability of data, which is an important consideration. Now, these high voltage feeders, to really be properly analyzed in the context of residential photovoltaics, we needed to add the low voltage networks. Now, this data is not data that was coming from OSNet. Actually, as a matter of fact, most DNSPs in Australia and around the world do not have electrical models of their low voltage networks and low voltage circuits. So we created what we call pseudo low voltage networks. So based on design principles and knowledge of number of customers, whereas the size of the transformer, we created the corresponding low voltage networks, so we can run unbalanced 3-phase modeling down to the connection points. And this is very important to capture really what is going to happen to the photovoltaic systems, to customers, etc., etc., etc. So it's very, very detailed modeling. Now, just some parameters, just for you to know more or less what it entails to model this network. So we're talking about, in a urban feeder, more than 3,000 low voltage customers, more than 80 distribution transformers, just 9 kilometers. So it's a relatively compact CRA21, the urban network. Whereas then you move into a long rural feeder as well, more than 3,000 customers, but then you have many more distribution transformers, 700. Why? Because you have less customers per distribution transformer. And this has significant implications when you have congestion of assets, because it means that if the assets that are going to be congested because of the rear power flow are transformers, these little transformers, you have many, many more little transformers to replace, and the cost of that can go exponential, and you will see this in the results. In this case, the long rural feeder has the farthest transformer is 50 kilometers away from the zone substation. So these are just characteristics for you to have a sense of these very different high voltage feeders that were modeled down to the customer connection point with these pseudo low voltage feeders. Now, the key findings of the traditional solutions and the non-traditional solutions. I'm not going to go into various details because this has been already presented in other webinars, and our reports are publicly available as well. But just to give you the context here, that then will take us to the next stages. Now, first of all, we modeled in all the solutions the Victorian, we keep calling new Victorian inverted settings, but actually they're not that new now, because that was in December 2019 that they started being used, or in effect, perhaps January 2020. So more than a year ago, but we keep calling them the new Victorian settings. Well, the thing is that these settings, they essentially, require not just a volt-watt settings, and naturally that implies curtailment, but simultaneously the volt-var settings. So the combination of reactive power with a management of active power according to certain voltage points. is extremely effective. It's a fantastic thing that was done by the Victorian government and the DNSPs here in Victoria, and I think something that should be pursued across Australia, because the use of the reactive power enables much more flexibility in the management of voltages, and that means less curtailment for everyone. So it is great. Now, that doesn't mean that necessarily with that, suddenly you will have a massive ability to have 50% of houses with photovoltaics. Unfortunately not, you still have problems, all right? But still, it is much more promising, definitely for other DNSPs outside Victoria. Here in Victoria, well, those settings are already being used, so it is great. Now, leveraging the on-load type changer at the some substation and offload type changers is something that already these DNSPs are doing across Australia, and definitely that's something good, and does bring benefits as well. It can allow you to go, if you already have the Victorian settings, it can allow you to go definitely at 20% or even a bit more, and the voltage magnitudes in terms of the voltage rise is relatively small, so it's quite good. You can push things really beyond 20%. And of course, what we realize with the traditional solutions is that augmentation is great, it is needed, but in the cases of the networks that we analyze, the benefits in terms of voltage are really minor. So therefore, augmentation will be needed eventually in combination with different things, but not on its own. On its own will not be able to deliver voltage benefits, only, well, the congestion benefits in the sense of mitigating congestion issues. So already with task 3, what we realized is that we will need a mix of solutions. With task 4, where we investigated non-traditional solutions, the first thing that we saw is that by tailoring volt-watt and volt-var PV settings, so these tailored ones is really making curtailment the moment that we reach 253 volts, which is 1.1 per unit, which means is that voltage is statutory limit across Australia. So the moment that you do that, because the Victorian setting allows you to go a little bit beyond that, the moment that you go stricter, is highly effective in mitigating all voltage issues. Now, the most important thing here of this finding is that most people might think that because now you are being more strict with this voltage setting of the inverter for the volt-watt, suddenly your levels of curtailment are going to be massive. No, actually the levels of curtailment when combined with the volt-var settings are not that big. So it's actually something that we should pursue, and we shouldn't be afraid of pursuing, but little by little, I guess. Then investigating the use of low voltage on-load type changers, which is a technology that exists already, is available, commercially available, but still not used widely. Very effective. Of course, combine as well with augmentation, combine with offload type changers when needed, because not all the time you need the on-load type changers in the low voltage. Very effective in managing voltage. Very effective, definitely. And of course, the moment that you combine anything with augmentation, you just cover everything, all the aspects, congestion and voltage problems. Batteries, off-the-shelf batteries. These are the normal batteries that we can buy today. Unfortunately, they are not more effective than the traditional solutions. Why? Because batteries with the control strategies that they come right now, which is essentially for self-consumption, which is great for the end customers because it reduces electricity bills. It's great for the end customer, but from the network perspective, the batteries will get full during the day, all right? Because they just absorb any excess generation. That means that at some point it gets full, let's say at 2 p.m. or 1 p.m., and then the photovoltaics still export. And that means you still have the same problems as a DNSP. You see the network with voltage rise and with congestion issues. So unfortunately, batteries as they are right now, not great. They might help a little bit, but not as much as one would expect. And this is where we propose, a network smart battery or network friendly strategies. And then this is where, we can unlock a massive amount of flexibility that can help significantly the networks and still provide benefits to the end customers who is actually buying this technology. And then the last non-traditional solution that we identified, that is something that is already being used by AusNet and other DNSPs in Australia as well, is dynamic voltage target at some substation. So this is either using a smart meter data in the remote parts of your high voltage feeders, or even a proxy of what is happening in terms of the whole reverse power flows or the flows at the head of the feeder to determine what might be the amount of generation that is happening at a given moment in time. And with that, of course, adjust the voltage target of the substation. This is a very effective solution when it comes to voltages. But of course, we still have problems of reverse power flows in terms of congestion, so it has to be combined with asset replacement, with augmentation when needed. So those are the key findings, but really what we learned was that from task 3 and task 4 is that eventually we need to form what we call complete solutions. And these complete solutions are essentially just the mix of different traditional and non-traditional solutions. So we identified these 7 solutions that are very similar to what we were just explaining, but these are complete solutions. So each complete solution mitigates both voltage and thermal issues up to certain penetration, of course, because they cannot do for all penetrations. Only some of them can actually go even for 100% penetration. You will see the results in the next slides. So the first one is off-voltage changers plus augmentation plus the Victorian settings. So off-voltage changers, changing the position has a cost, of course, to it, because you need to disconnect the transformer. You need to put a genset or something, to continue giving power to those houses. But once you change this, and it's something that DNSPs are doing across Australia and across the world as well, when they use this technology that exists in most cases, it's very effective, but it has limitations, of course. But it is a good solution. Playing with the zone substation OLTC, so changing the target with just changing it, for instance, from 1 per unit of target to 0.98, so lowering the voltages all the time, can be to some extent effective, but it also has limitations. Then we go into the Taylor volt-watt and volt-bar settings as well with the off-voltage changes and augmentation. This one is quite interesting. It's really effective and really doesn't affect customers that much. Then we have the low voltage and low voltage changers that combine with augmentation as well and other technologies also can be very, very effective, but of course the question is cost. Off-the-shelf batteries as well with augmentation, effective, but much more effective, network friendly or network smart batteries as well. And finally, the dynamic voltage zone substation combined with augmentation and off-voltage changers where needed, they can become very effective. So the moment that technically we see them where they are effective or not up to certain penetrations, and depending on the type of network, the next question is cost as well. All right. So let's see first the technical performance of these complete solutions. So we have here these ticks that represent, how many networks actually they were able to cover, and also what penetration of photovoltaics. So what you see here very quickly is that, for instance, the Taylor volt-watt and volt-bar setting plus the voltage changers augmentation can really deal with up to 100% penetration with all the 4 networks, which means it's a solution that we can implement today and be future-proof if you want. But of course, there's a cost associated to it because augmentation means we have to replace transformers, etc., etc., etc. The low voltage and low voltage changers as well with augmentation and off voltage changers, and also the Victorian settings, of course, can go up to 100%. Network smart batteries as well. Dynamic voltage zone substation, we did it only for 1 network, the urban network CRE21. It was very effective. We believe that it can happen actually 100% with the other networks. However, there are other solutions that might be effective at certain penetration levels, but not necessarily up to very, very high penetrations. So that's the off-voltage changer. It's very effective, up to 40% penetration for some 2 of the networks, or even 3 at 20%, but the higher up we go into the penetration voltage, it's no longer effective. It's just not capable of having enough flexibility when it comes to managing voltages, particularly because augmentation is doing its job, but voltages cannot be managed. The zone substation, just moving the target a little bit lower, again, it's also limited because you don't have a lot of flexibility there. So it's really the other more flexible ones. Off-the-shelf batteries as well at 100%, we have problems as well. So technically, we can say it is doable. So the moment that you know which penetration is going to be really the most realistic future of a given network, we can pinpoint which one are the most effective solutions from a technical perspective. But the question then is at what cost? And then this is where we continue with Will. Will, please.
Yes, thank you, Nando. So yeah, as Nando said, we now need to start thinking about how much are these solutions going to cost. We have many solutions, but of course we need to think about what timeframes are we needing these solutions for, and at what timeframes and penetrations we then compare them. So in light of that, we split the analysis into 2 main areas: the short to medium term. So this is a reasonable time frame, so 40 to 60% penetration. So, 10, 20 years from now. And beyond that, we might start encountering uncertainties in terms of the DER technologies, electric vehicles, that kind of thing. But for completeness, we still have long term. So this is beyond 60%. This is looking to, okay, what is the cost now if we want to reach 100%? Okay, yes, we admit things can change between now and 100% PV, but if you want to plan for the future, it's a good idea to have an idea of the cost it will take to reach 100%. And also importantly, what solutions can reach 100%. You don't want to invest today and then maybe you regret your decision once you've hit 60% because you now still need things for the long term. So the analysis is split into the short to medium and the long term. And then for the feeders, we had a forecast from AusNet on the forecast of PV installations for each HV feeder. So for Longroll, the HPK11 and KLO14, they all had the same forecast of PV uptake. And then CRE21 saw a much greater uptake historically and predicted into the future. So the timeframes are a little shorter for CRE21. So if we could move to the next slide, please. So when we talk about costs, obviously there's some considerations we need to make when we're comparing costs. So firstly, we use net present value. So this is simply to compare costs for the future, and we can discount them to the present day cost. So, we're talking about investments that we might make 10, 20, 30 years from now. If you take that money today, invest it, and then spend that money, it will cost you less. So that's the idea of accounting for net present value. And also within that, you can account for the effect of inflation, which acts against that, making things more expensive. Furthermore, we then obviously have the cost of assets. Now, this can be split into three broad categories: capital expenditure, so the assets, basically installing these assets, so transformers, tap changes, replacing conductors, the control logic and systems required for that dynamic voltage target that Nando was talking about. All these require capital costs. But of course, you have operational costs, so changing the offload tap position of these LV transformers, the traditional solution. That's operational expense because you already own the asset. You need to go and change some settings on that, and also a potential maintenance of on-load tap changes. And finally, we have the cost of PV curtailment. So how much will it cost the customer ultimately, who will be paying these electricity bills? How much will it cost them if they have to curtail? So for that, we use the Victoria minimum feed-in tariff, which I think is about 10.2 cents. And also in deliverable 5, we also considered half of that. We won't be presenting that today. And finally, the year of installation. So like I said, we're considering the short to medium term, long term. This means assets might be installed 10, 20 years from now. So we need to think about what year these assets are going to be installed. So to tackle this, we obviously, when we ran our simulations, as you saw in 20, 40, 60, 80, and 100%, we ran them in set years. So what happens between these windows, we haven't simulated. So therefore, if at 60%, we need to replace 5 transformers, then it needs to happen before then. So the next window was 40%. So we say, okay, let's replace the transformers the year after 40%. So let's say it's 2030. Okay, we'll install them at 2031 so that by the time we get to 2040, we know it's going to be okay. And this way you get the maximum discount through installing them as late as you can. So the earlier you install them, the more it will cost you. So you want to install it as late as you can get away with it, but also being conservative in that we replace these assets before problems occur. And that's a really key aspect to think about, is when you need to install these assets. So if we can move to the next slide, please. So now when we put all this together, we can start comparing costs. And so this is a summary of the work in task 5 that was then presented in task 6. And we're looking at the short to medium term. So that's a 60% PV hosting capacity across our 4 networks. So what we can really highlight from here is that if you look at solution 1 and 2, the traditional solutions, they are very cheap. And that is why the DNSPs are doing that today. For the current hosting capacities we have today, they're a very cost-effective solution. However, yes, Series 21 at 60% they work. The other feeders, we start running into voltage problems. So you need to look elsewhere for these feeders, and certainly for higher PV penetrations. So we can also see that the stricter watt and volt var settings, they're really quite excellent value for money, and they work across all these feeder types. However, if we look at the low voltage on-load tap changes, very expensive. Why? Well, we're now talking about replacing distribution transformers with on-load tap changing transformers. So this means that you have to replace a device to solve voltage problems. So even if the cost of an OLTC was equal to the cost of a normal transformer, you have to replace, tens, hundreds of transformers in rural networks, and that gets very expensive. So if you could look at the cost of on-load tap changes in rural networks, 64 million, 100 million. This is because, as Nando said, there's many more transformers per customer. So the cost really starts to skyrocket when you're having to replace many, many transformers just to solve the voltage issue. So that's very much more suited for urban feeders. And then, as we can see, off-the-shelf batteries it was also quite affordable, but we run into limitations quite quickly. And when we use network-friendly approaches like network smart batteries, we can see it works across all the feeders. And not only that, it can be significantly cheaper. Why? Well, this is because if you can manage your asset congestion issues, you don't need to augment. So for urban networks, it was found that really the only cost was changing the offload tap positions, tiny bit of curtailment, but almost none. And so by limiting the levels of reverse power flow, you need to augment less, and you can also manage voltages. But for rural feeders, the network smart batteries weren't as effective in managing asset congestion, so some augmentation was still required. And this led to the tailored settings actually being cheaper for rural networks, whereas the network smart batteries were cheaper for urban networks. And finally, we can see here that the dynamic voltage target at the zone substation OLTC is sort of a great middle cost option. So, if you can't have stricter inverter settings, you can't have network smart batteries, but you want a good reliable solution, the dynamic voltage target is a good sort of middle cost option. Finally, as you probably expect with the type of networks, urban is significantly cheaper than rural networks generally. Obviously, it differs solution to solution, but typically this is down to the augmentation required and the number of devices that need to be replaced. So if we move on to the next slide, please. So now we can compare the costs for 100%. So instantly you'll notice that the traditional solutions 1 and 2 no longer work even for the Series 21 urban feeder. So we now really need to look towards the non-traditional solutions if we want every house to have a PV system. So again, the strict inverter settings work for all feeder types, and so does the network smart batteries. So again, we can see even for 100% for urban feeders, the network smart batteries are very low cost. The only major cost, the offload tap changes and minimal augmentation. Then if we look at the on-load tap changes, it gets very expensive as before. And we can see that rural in general is more expensive than urban. And the dynamic voltage target, again, is a good middle cost where if you can't really do the others, it's not that much more expensive, but you still get excellent benefits. You may be wondering, why is network smart batteries so cheap if we're involving batteries? This is because we're assuming that the customers are installing these batteries and that they're required, if they want to install a battery, they would have to, similar to how inverter settings today, a customer buys a PV system, they then must adhere to a connection standard if they want to connect. It's the same thing with batteries in this case. So the customer buys the battery for their own reasons, but if they want to connect it, if they use a network friendly type approach, you can get a very cheap solution to a very high hosting capacity with very little augmentation requirements for urban networks. And for rural networks, it is a little bit different. Finally, the KLO14 you can see is the most expensive feeder. This is down to conductor costs. So that required significant amounts of HV conductoring, which really push up the cost. So any solution really has to replace those cables. So it will always be the most expensive feeder, even with the network smart batteries in this case. So if we could move on to the next slide, please. So here, just as a sort of little mini summary, we can see them side by side. Obviously, in terms of pure costs, the cost will increase for 100% because we have more assets to replace. But in general, we can see that if we continue with this new approach of dynamic voltage targets at the zone subs, there is great value in that where we can do it. It's a good middle cost solution. It's easy to implement. Furthermore, if you can, there's great value in the stricter inverter settings. You can see really significant cost savings, and regardless of the type of feeder, you're going to be able to get 100% hosting capacity because of the embedded settings in the inverter. You're not going to go above 1.1 per unit. And if you combine that with augmentation for any asset congestion issues, you're pretty much set for any feeder and any hosting capacity. And finally, or second to last, if network smart batteries are excellent if you can get them in the penetrations that you require, and if you are able to coordinate your batteries such that they are adjusting their charging in relation to how much PV generation that's going on, that's how they work, then you can really, in urban networks, almost eliminate augmentation costs and make them an extremely cheap feeder. So, you know, $59,000 for what is essentially thousands of customers is a very good deal indeed. And finally, it's very difficult to justify low voltage OOTCs. It's just the cost of replacing so many devices to solve voltage issues. It really does add up. So if you are going to use them, perhaps looking towards potential voltage drops in the future, that kind of thing, then urban networks are probably where they're best suited because there's fewer transformers to replace. So if we move on to the next slide, please, we can now see it in a slightly different light. So this is the cost per megawatt hour. So you simply look at the cost, you look at how much energy was generated in the period, and then we get a new way of comparing the cost per megawatt hour. So you know, this is a good way of comparing across networks and maybe to government agencies and things that are more interested in this type of figure. And in general, urban, as we expect, is generally lower than rural, again, because of the lower augmentation costs. And you see that the cost for 100% actually goes down. Pretty much is simply because there's more generation at 100%, there's more customers generating, and obviously there's a longer period of energy that can be generated as well. So yes, the costs of reinforcing the network for 100% go up, but when you account for the time frame that they'll be generating for and all the extra energy, it actually is cheaper per megawatt hour. And finally, you know, the dynamic voltage target at the zone sub is that great middle ground, even in per megawatt hour. And also you would think that perhaps a stricter inverter setting, you might be worried about the impact on curtailment. It's, you know, a slightly stricter inverter setting marginally increases curtailment, but not by much. And you can see that's reflected in the dollar per megawatt hour. You know, if we had silly amounts of curtailment, that cost would go right up when we don't. So it's still a great option. So yeah, if we could move to the next slide, please. So that's fantastic. I've bombarded you with many numbers and cost figures, and some solutions cost good and some feeders cost more than others, and solutions only work for some feeders, but not all feeders. So there's a lot to take in there. So it's all very interesting, but how do we boil this down into tangible actions DNSPs and other agencies and stakeholders can take when they're planning the future of their networks? So if I'll hand it back to Nando for some recommendations.
Thank you very much, Will. So let's get into the recommendations, all based on all the work that has been done from task 1 to task 5. So lots of text here. I'm not going to read everything. Perhaps some of the recommendations become very obvious after all the slides that we have presented and the comments that we have provided. So we divided the planning recommendations into short to medium term and the long term. So in the short to medium term, so trying to achieve in the next 20 years, more or less, around 40 to 60% penetration of hosting capacity, depending on the type of network, of course. So the first thing, for DNSPs across Australia. If they are not in Victoria, I would say adopt something very, very similar to the Victorian PV inverter requirements. These requirements should be emulated by DNSPs outside Victoria if not doing something similar. Why? Because having the volt-var enabled simultaneously with the volt-watt just brings much more flexibility in terms of voltage management from the perspective of the PV inverters. And then that overall means lower curtailment as well, not just managing voltages more effectively, but lower curtailment, which means more benefits to the end customer. They're getting more from their photovoltaic systems. Now, the next recommendation really is to continue exploiting existing assets. So what DNSPs are doing already, based on all the discussions that we have had with AusNet, based on our knowledge and feedback as well from other DNSPs, not just in Victoria, but across Australia and in other parts of the world as well, they need to continue to do the obvious things that they already knew what to do, like using the offload touch changers and changing the position as much as possible, or changing the voltage target at some substations. Instead of the 1 per unit, going to 0.98, meaning slightly lower voltages all the time. That is great. If we're looking to the short to medium term, that is something that should be done. It's very cost effective. Continue doing so. But then the next step really is really thinking, and I know that this doesn't necessarily depend on DNSPs, but then this is where, well, not just the DNSPs, but different stakeholders and government agencies, they need to consider the potential adoption of much stricter volt-watt and volt-var settings. So really, instead of allowing generation, like in the Victorian case and the Australian standard anyways, to go beyond 1.1 per unit for residential customers, meaning more than 253 volts, we need to stop at 253 and not allow further generation. But of course, this has to be combined with the volt-var. So it's not just curtailing, but curtailing in a clever way. Now, our findings show that really the added curtailment is not necessarily that significant. So this brings benefits to both customers and to the network. So this is something that should be considered, hopefully in the next few years. And by any means, there are already standards around the world that are as strict as what we are proposing here. Now, moving on, implement intelligent voltage control at zone substations. This is what we were calling the dynamic voltage control of zone substations. AusNet has already trialed very successfully this in some substations. They already know the technology, they know the cost involved, and this is something that other DNSPs as well are trialing with or without smart meters as well. So it is something that you should continue exploiting, and it is great. It's something that is entirely under the control, if you want, of DNSPs, and it's something that they can take an action on. It's an asset that they know very well, so it's something that should be exploited. Now, when it comes to other technologies, and these recommendations, the way that we put them in the report and here in the slides, is really considering the practical aspects. So this is why we didn't start with our first recommendation, use network smart batteries. Despite all the numbers that you have seen there, the network smart batteries or network friendly batteries are fantastic. They really can bring massive benefits to both customers and the networks. The reality is that for these benefits to be tangible, you need everyone with batteries. And that is not going to happen. That is not going to happen in the next 5 years, all right? However, it might happen in the next 10 years with or without subsidies from governments. But because it is going to happen eventually, and the benefits are very, very big if we actually have the right connection requirements for the batteries, rather than just self-consumption mode as they are right now, then there's an opportunity in the short to medium term for DNSPs to champion adequate battery connection requirements. I'm aware that this is already in discussions between DNSPs and the government here in Victoria. I'm not aware of what is happening outside. However, I think that there's a very, very interesting opportunity here. However, this is about pursuing the requirements and defining the requirements. The realization of the benefits will be seen only in the long run. Other considerations. Well, in terms of the low voltage on-load type changer transformers, what we have seen is that they are very, very expensive compared to the other solutions. So at this stage, considering that we're looking at photovoltaics really more than electric vehicles in the next 5-10 years, then perhaps on-load type changers for the distribution transformers is not adequate. But in the future, with other technologies being connected, particularly electric vehicles, this might be different. So let's move to the long-term planning recommendations. Definitely, we need to adopt a stricter volt, watt, and volt bar settings. The benefits are significant, and the impact on customers, meaning the curtailment, is not. So we should go for this in the long term for sure. I know that this requires it's not something that the DNSPs can actually just simply say as a connection requirement, but it's something that has to be pursued definitely. And well, in terms of the intelligent control, voltage control at source station is something that should continue, because we believe that in many cases, although it's not gonna really be applicable to all type of high voltage feeders, because it depends on what is the characteristics, but in general, it's something that should be pursued as well for much higher penetration. So in the long run, intelligent voltage control at source station is something that should be pursued as well. And when it comes to batteries, well, at this stage, if we're looking really, 30 years from now, more than 20 for sure, well, we see a future where, well, batteries are going to be more present. But if these batteries didn't have connection requirements that were, let's say, more network friendly, well, this is a missed opportunity. So we should exploit that flexibility in the long run. But for us to exploit in the long run, we need to have the connection requirements established now, in the next year or two. Otherwise, we will miss the train. We will miss that opportunity. And other considerations here, again, even in the long run, our numbers that were presented by Will in terms of cost show that the low voltage, the on-load type changer transformers, the distribution transformer with on-load type changers, they were very effective technically, but very expensive. However, what we cannot, I don't want you to have as a takeaway the on-load type changer transformer for distribution transformers are not worth it. Well, I mean, we did not consider in all our analysis electric vehicles. And depending on what is going to happen in the next 5-10 years, they can increase in numbers significantly, as it is happening in other countries. And electric vehicles being demand, they will push the voltages down, all right? So now you're going to have, during the day, photovoltaics having reverse power flows with voltages going up, and at night the voltage is going even farther down than our usual peak demand. So then in those cases, you need technologies that help you managing the voltages that are going up and down. And then this is where this technology can actually be extremely effective, and definitely technically will be effective. But the question will be where it is cost effective. We didn't consider electric vehicles in this analysis, so we cannot say much more than that. It might be an opportunity there. So those are our recommendations in terms of planning, but we also consider in the report other recommendations related to analysis. So what if the DNSPs or other stakeholders would like to do similar comparisons to what we did in this project? So these are the recommendations for advanced PV hosting capacity calculations. I'm going to go relatively quick here because this is very technical for those that do modeling, but still just for completeness, I'm going to just spend 3 minutes here, and then we can conclude and go to the questions. There are a few there, and certainly there will be more. So model-based approach, this is what we did for most parts of the project. That means that we had the network models, the electrical models, we put it in a computer, software, we ran power flows, we did time series analysis, et cetera, that allow us to quantify all these. So it is a very well-known approach. This is what DNSPs do every day. Planning engineers there, you know this very well. Perhaps not necessarily in time series manner, not necessarily as sophisticated in terms of stochastic analysis, or well, it's having uncertainties, but still the model-based approach is something that is very well known across the world by DNSPs. However, there are other approaches as well, and this is what we did in task 2 that we didn't mention earlier. So in task 2, we investigated innovative analytical techniques. I'm not going to go into the details here, but what we came up with is that for those DNSPs that have smart meter data, particularly those in Victoria, of course, there's an opportunity to extract, of course, following what we propose here in this particular report, to extract, maximum voltages per distribution transformer of the corresponding customers, and compare this with the corresponding aggregated power of the net demand at the corresponding distribution transformer. And there's a correlation that is very strong that can allow you to determine more or less what will be the potential hosting capacity of that network. For that, of course, you need data. And with this data, you do a regression analysis, which is what this slide is trying to show. But our studies suggest that this can be a very effective way of not doing the analysis running power flows, but just using your smart meter data. You can have a very good guess of what is, I wouldn't say a guess, a very good estimation of what would be the hosting capacity of that particular network. So it is possible to do this, but of course, you would need to implement it. And we didn't implement it in this project. It was just a study based on simulations. So our recommendations for those of you that would like to carry out advanced calculations, such as what we did in this project, for the model-based approach, definitely you need to consider low voltage feeders. This is not common yet for DNSPs in Australia. I'm aware of a few that are already having models on low voltage feeders. Evo Energy in Canberra, for instance, they have everything modeled actually down to the customer connection point, which is fantastic. But it's not the case of most DNSPs in Australia and in general around the world. But if we really want to quantify things properly at the connection point, we need to go down to the connection point of residential customers. So we need these integrated high voltage, low voltage network models. So more work is needed. But if those electrical models cannot be precise, we can use pseudo LV feeders, such as what we did in this project. And well, all the corresponding, let's say, recipe of doing that is also reported in our reports. And definitely we need this to perform time series simulations. Otherwise, we will not capture the time dependencies. So not just of the control elements, but also, what happens in terms of energy curtailment for the customers. And that is important to quantify if we want to understand what are the effects on customers. We need to cater for uncertainties. So PV location, PV size, irradiance profiles, this can be done as well, and this is needed. And other considerations, of course, sometimes, if we want to understand what are the benefits of a given solution, we don't need to model all our high voltage feeders, but we need to consider the most important high voltage feeders based on several characteristics. And we can, what we suggest is to do something like we did in this project, which is really looking at the extreme cases, because if in the extreme cases you can quantify what would happen, or what would be the benefit of a given solution, then any case that is in between, of course, the solution will work and will be much cheaper for sure as well. So identifying the most extreme cases is something that can actually help as well, understanding the spectrum of the benefits of a given solution. Now, when it comes to smart meter driven approaches, which is task 2 that we didn't discuss a lot, but I just wanted to mention that any DNSP that has access to smart meters, I think that this is an interesting opportunity, but they should run trials, of the approach that we're proposing here. They should have data that covers minimum PV penetration increase. So, for instance, I don't know if they know that there's an area that has had in the last year an increase of 20% penetration, then that's the list that we need, for this data to be useful. Less than that, if they have data of a network that doesn't have photovoltaics, and it's very difficult to actually predict what would be the hosting capacity. And finally, of course, in terms of the smart meter driven approach that we propose here, well, we noticed that OLTC actions, from the substations can actually affect the accuracy, but that is not necessarily that significant. At the end of the day, if it is an approach to quantify hosting capacity in a very quick way, just using smart meter data, I think it is a pretty decent trade-off. All right, just to finalize here, we're doing 60 minutes of presentation. So all our reports are publicly available. These are all the links there. We will provide this presentation as well to all of you, the webinars as well, and this webinar as well will be available in our project website and YouTube, so we will provide all that. So before going to the questions, just I would like to thank again ARENA for the funding, OSNet for the funding, but also for the collaboration. Tom, Justin, John, Vinodini, thank you very much for all your time and your effort in contributing to this project and sharing your knowledge. And also thank Andreas and Michael that were, well, Andreas was part of the University of Melbourne, Michael still is, they supported as well this project. And well, thanks Will as well for all your hard work as well on this. And with that, thank you very much to all of you for attending this webinar. I'm more than happy to answer all your questions. Thank you. All right, so let's start here with the questions, Will. please feel free to use the chat if needed. I'm going to go to the questions here. Peter, thanks for your contributions. So for traditional storage, there is also load generation balancing between phases. That is correct. That is something that we did not consider here because of the amounts of photovoltaics and the uncertainties that were there in terms of the analysis that we did. But that can also actually be done as well, the balancing between phases. However, although it is not part of the analysis that we carried out, in terms of the analysis that we have done within the university, although there's an advantage in balancing the installations of photovoltaics, this advantage is only seen in relatively modest penetration. So what I'm trying to say is that balancing photovoltaic installations, or in general flows, balancing flows, is very helpful up to 20, 40, perhaps 50% of photovoltaic penetration. Beyond that, the voltage rise is so high that not even balancing will help. You will have problems. Perhaps the problem in terms of the magnitude might be lower by balancing, but the problem will still appear. So that's important as well to mention with balancing. Sorry, I cannot present the results, Peter, but I promise that I will show you these results in a few months. We already have something interesting to show. Now, moving on to another aspect that Peter is mentioning here is that using load to absorb excess PV generation. That's absolutely right. That technique hasn't been used here because it was behind the meter, and the only thing that we could consider here behind the meter is just the standards on the PV inverters and the batteries. So trying to avoid more futuristic, let's say, approaches, because it's very difficult to understand the technicalities and the corresponding cost. But yes, of course, managing load, if someone could do that, that would be great as well. Another question, does a network model takes into account of load addition to network impedance, transfer line? What is the assumption with regard to load modeling? So in terms of the loads are modeled as constant power, so PQ loads, so directive power is there. This is all coming from a pool of smart meter, anonymized smart meter data that represented houses that would be seen in these particular networks. So this is actual very realistic data. I wouldn't call it real data because it's real, but it's not real for those networks. So it's just coming from a big pool of customers. In terms of load modeling, well, repeating that is P and Q, so it's constant power. So you can argue that, I mean, an adequate model would actually reflect as well the changes in voltages and the changes in demand. But we didn't do that. We know how to do it, but that would be adding too much complexity in this particular study. The effects, however, in voltages will still be seen with other load models. In network smart batteries, does the DNSP or customer pay for the battery cost? Oh, that's the customer. So this is just assuming that there's similar to the PV inverter settings, we can actually set a standard for the batteries. And if the standard is such, like what we were proposing in this project, this network smart battery or something similar, then those are the benefits that you would get. But the battery is being bought by the end customer, the house. Sam is asking, were high voltage line regulators considered? Yes, actually, as a matter of fact, we have all these networks here. Modeling them were not easy. So here you can see here, actually, as a matter of fact. So for instance, the long rural, you will see that we have capacitor banks as well. So sometimes you have, for instance, a regulator as well in the middle of the line. So this applies more to rural. Urban are pretty simple. Just the only regulation point of voltage is in the zone substation, but the rural feeders are those that have the capacitors there. So we were considering all that. You can argue as well that we could, I mean, the moment that we have high voltages, you can remove the capacitors and then you just don't use them. So you don't have higher voltages. That we didn't do, all right? So that becomes a very case-specific sort of solution. But we just kept the network as it was with their capacitors and other things. What cost did you consider to, that's a question from Michelle, to be attributed to the DNSP in relation to network-friendly battery connections? So as I mentioned before, so the actual battery is being bought by us, the end customers, but the cost then to the DNSP is still augmentation. So as much as even network smart batteries are there and they help, the moment that you have a significant number of houses still with photovoltaics, there will be reverse power flows. And eventually these reverse power flows will trigger the need for replacement conductors or transformers, particularly distribution transformer most of the time, and particularly in rural networks. So that is something that the DNSP still has to bear with. But in terms of the battery itself, no, zero cost, similar to a photovoltaic installation. It's bought by the end customer and they just have to follow the standard. So similar, that's the sort of thinking that we consider for the batteries. If people buy it, they just have to follow the corresponding requirement or standard. Peter is asking, United Area has implemented high voltage management system. Yes, that's correct. United Energy is one, and I believe that they were, if I'm not wrong, they were using the smart meters, which is great as well. So this is very accurate because they will just move according to what they're seeing with the smart meters. In OSNet, they were doing it just with measurements at the head of the feeder with the flow as a proxy of what supposedly will be the generation at that moment in time. So it's a proxy, but actually it's very effective as well. So yes, it would be very interesting to hear what their results are so far. From United Area, I'm not aware, to be honest, although there might be some reports, but OSNet seems very, very happy with the results that they have seen with the implemented technique. MAH13A is asking, what do you think of demand response potentials? I think that the demand response has a massive role here, but again, similar to what I was mentioning earlier, demand response, as the name says, demand, requires someone to take an action on that demand. It can be the household itself through some sort of direct or indirect control, or it can be an aggregator. But whatever it is, it requires another layer of complexity to coordinate all of this. So this is more related to what we are calling orchestration of distributed energy resources. And then therefore, because there are still many technicalities and cost aspects that are just simply not known, because these are all trials and potential solutions in the future, it would be very difficult to compare them here. And that's why we didn't consider them. But technically speaking, yes, there are many opportunities, similar to what Peter was saying earlier about, for instance, managing the hot water loads, when there's a lot of photovoltaics. So yeah, there's a lot of room for that. But the problem is, how do you quantify the cost of those technologies when they are actually not yet known? And finally, Peter is sharing with us a standard here that should regulate their supply voltage within 230 plus 6% plus minus 2. Okay, so this is a proposal, Peter, to allow for voltage rise and voltage drop heavy consumption. All right, so they are trying to lower the voltage limit, the upper voltage limit. Benefit of plans efficient legit. I wonder what would be the hosting capacity. Oh, Peter, that is an interesting. Thanks for sharing that. Okay, this is not good actually, to be honest. I don't know why they are doing it. my personal suggestion here is that actually, if at all, we should increase the voltage limits. Actually, most of our appliances today, they are all power electronic related components, so they actually adjust to voltages. And then therefore, it means that before, many decades ago, when we saw voltages going down, we would see our incandescent bulb, being less lit, or our tellies even, going smaller. But today, we don't see the effects because our appliances are pretty robust with voltages. So if we really want to see not just photovoltaics, but also electric vehicles in the future, we shouldn't tighten these voltages. Actually, quite the opposite. We should be more relaxed. That would be my gut feeling, Peter. If they decide to tighten things, I think there's also, this other school, of thought that clearly they are saying that there are benefits for efficiency and longevity, but then we need to find what is the trade-off. Having that regulation very tight will mean much harder. Achieving the hosting capacity that we're quantifying here will be much harder, and that only means to me very clearly more curtailment. So there's no way that we will have much more photovoltaic generation with tighter voltage limits without curtailing significantly. So that will be the impact. So in terms of achieving that, plus 6% minus 2%, technically doable. Cost effective, well, it's going to be perhaps more expensive, but not necessarily because of the assets that are going to be needed, but I think because of the curtailment, and that is a cost at the end of the day, because people will not get the return on investment as they were expecting. So interesting proposal. I cannot say more than that for now, but very interesting proposal. Just to complement that information, Peter, actually, as a matter of fact, in Britain, there has been already lots of discussions about loosening the voltage limits as well. So quite the opposite from what is being proposed there. I can understand the pros and cons of each of them, but someone has to do the corresponding analysis to really make the best decision. Well, if there's no further questions, well, I'm more than happy to answer any other questions. The chat is there. Also, feel free to unmute yourself. You can now you have the ability to unmute yourself if needed. Any questions or comments? Okay, there's Peter.
Yes, Professor Nando, I just want to probably comment on the last when I talk about the voltage. I think that's more from an appliance efficiency perspective, because when someone designs an electrical appliance, you have a certain efficiency in mind, and it's very difficult sometimes to achieve that efficiency at a very high voltage range. So because most of the nominal voltage now in the world are 230, so a lot of appliances now are being designed for 230 to be optimally efficient. So from the efficiency perspective, I think there is an angle to look at that. We should be lowering our voltage towards that range, rather than actually at a high level that we have right now. I think that's really driven from that perspective of appliance efficiency. And I think the other thing that I need to sort of clarify is that when we talk about the 230 plus 6 minus 2%, that's in the absence of PV. So essentially saying that if there's no PV, if you regulate that to that level, then you've got 4% that allow for voltage rise under that situation. That's really where you sort of come from, that idea.
All right, and thanks for adding that information. Yeah, but then that is quite challenging, because how do you know there's no photovoltaic at a given moment in time? Not because you don't have photovoltaics in your home, it means that your neighbor might not have. And so it's very challenging how it would be implemented. I understand that the point of being more efficient with appliances, and I think that we need to consider that as well. But I guess the big question is, what is that we want to achieve? If by being efficient with appliances, we are reducing our electricity consumption, and we are also making our appliances more durable, and then therefore we are reducing waste, how that this compares to allowing much more penetrations of photovoltaics? I don't have the answer. What I'm saying is that this needs to be quantified to some extent, I guess.
Yeah, agree. Yeah.
Thanks for that, Peter. There's a question here from Robert. If you implemented a stricter PV settings, customer solar would ramp down even if the voltage at the POC is compliant. That is correct. Yes, there will be more curtailment. That's true. The customer's load might also be higher than the solar output. That can happen, of course. Do you think this would be palatable for a customer? With certain customers at the end of the circuit there are two very interesting questions. So stricter PV settings, these are already settings, there are standards. I don't remember off the top of my head, happy to provide that information later, but there are already standards in the world that are as strict as do not go beyond the corresponding local limit. So this is not new at all. Is it palatable? Well, at first I would say no, but hey, at the end of the day, we all are imposed limits for the benefit of the corresponding network. We have fuses, we have different things, we have to follow standards. So at first it might not necessarily be palatable, but what our studies are suggesting is that even with that stricter limit, combined with a volt bar, of course, that both have to be there, the added curtailment that we quantify with all these 4 feeders in total would be more than almost between 12 and 15,000 customers, is that the added curtailment in average is just 1% more. So it's not really that significant. Why? Because this happens only in those days where there's no one at home, so very little load, and there's a lot of generation. But those days are not the 365 days across the year. So that's the first thing. So I think that there's still benefits, and it is, I think, more palatable at the end of the day, because technically speaking, by allowing this more stricter curtailment, it means that eventually the DNSPs will not need to invest in further reinforcement or other technologies, and then therefore we will see electricity costs going down. That's the expectation. Now, the second question, Robert, here, with certain customers at the end of the cycle with barely any output from the solar, that is a very, very important question, because now we're looking at the fact that two customers, one next to the distribution transformer and one at the very end of the feeder, with the same setting. So forget where it is a super strict or is the Victorian setting or just the Australian standard. In any of those cases, the customer at the very end of the feeder will have more curtailment. Why? Just because of the physics of the network, because of the impedance. The voltage rise that these customers at the very end will see are much higher because of the impedance there. So any injection of 1 kilowatt to the network will have more effect on their voltage than the 1 kilowatt injection of the customer next to the transformer. That is unfortunate. That's how these local settings work. But as I was mentioning earlier, the average effect is such that it benefits most customers. But yes, you will see more curtailment in those customers at the very end. How we address that? Well, that is very difficult with the standards that are for the device, rather than looking at a much more comprehensive way of sending settings that are more fair to all customers. The latter, what I just mentioned of sending settings, is aligned with orchestration of photovoltaic systems, or in general orchestration of distributed energy resources. That requires another layer of complexity, technicalities, infrastructure, and cost that, of course, we didn't consider here because there are many unknowns. But well, bottom line, yes, customers at the very end will suffer more of curtailment. Disregarding the stricter settings, can be the Victorian settings, can be the Australian settings. Thank you. Any other question or comment? Feel free to unmute yourself as well. Now you can do that if you wish. Okay. Will, any final comment or something that I might have missed?
No, I think everything was covered there. Yeah, bottom line is many options to consider, what's realistic, and yeah, I think there's some pretty concrete recommendations there in accounting for what can actually happen.
Very good, thank you. Well, if there's no further questions, of course, our emails are there. More than happy to follow this up as well. Thank you very much, everyone, for attending this webinar. I appreciate that it might have been during your lunchtime as well, and we're getting busy, of course, as the year progresses. Again, thanks to Arina, thanks to Osnet, Tom, Justin, John, Vinodini, Andreas, Michael, and Will. Again, thank you very much, and thank you to all of you, for attending this webinar. And we will follow this up with the corresponding links once everything is available online. Well, thank you very much. Have a good day and a good afternoon. Bye-bye.
Thanks, guys.